Okay, let's pace to get started with the next session. We are a couple minutes behind, but we should be able to make the schedule anyway. So let's get people back into the room at the tables. Just walk in. We are all friendly here. Richard, we are about to start. Gordon, Bob, out there. France. We are starting again. See David coming. Very good. We are almost back to full attendance here. Okay, very good. Let's get started then. So let's get those people on the live stream back up. And we are ready to start the second block of presentations. Welcome everyone back. We'll have, I think, and at this point you might think that it might be difficult to match the two excellent presentations we had before. But you'll see that you might be wrong. We have a great block of 4 presentations coming with a lot of good content. So without more preamble, let's get started with the first one. We have, first of all, someone with a company. When you come up with a name for a company, sometimes you need to be careful in understanding the long run of it, right? And initially, you might think that a particular data format might be a good name for a company. So you might call your company Logi XML. But then soon you realize that you need to use also CSVs and other JSON formats. And then Logi XML might not seem that appropriate. And you can be changing your name over and over, right, every few years once there is a new language or a new data format out there. So you just stop it there and call it Logi Analytics. So we have our first presenter in this block, who is Anthony Gill from Logi Analytics. He's going to be talking about the integration that his people, his team, have done on HPCC and their great analytical platform. So welcome, Anthony, to the stage, please.
Hi, everybody. My name is Anthony Gill. I work with Logi Analytics. And as Flavio said, I'm going to be talking today about how to integrate business intelligence with your HPCC system. So as we go through this, we're going to go through a quick introduction about who Logi Analytics is, formerly known as Logi XML. And yes, that probably was a bad name. Not really foresight there. But you know, it is what it is, and we changed our name to Analytics to actually showcase more about what we do. After I go through that little introduction, we'll go through the continuum of self-service. This is a framework that we use to build out business intelligence apps. So we work with a variety of different customers, sit down with them, try to figure out what they want to do, and then we'll move forward from there. Finally, we'll actually go into a demo, and that's actually why I have my laptop up here with me. We'll be doing a live demo of an application we built leveraging Logi Info, one of our platform products, integrated with HPCC. as well as Logi Vision, one of our discovery products that's also been connecting to HPCC as well. So first, a little bit about Logi Analytics. Again, we were known as Logi XML a little bit about 2 years ago. We changed our name to Logi Analytics, and it's been pretty fun. So I've been with the company about 4 years. I lead our solutions engineering team that deals with software vendors as well as enterprises trying to build out their BI software. We have thousands of customers across all different types of verticals. Again, this can be software providers, or it can even be the enterprise, or even small mom-and-pop shops. So the smallest company I've worked with was 2 people. The largest company I've worked with is a few thousand. So we work with a variety of different customers there. And here's a quick snapshot of some of our customers. So you can see that we have a lot in the financial services industry. We have a lot in high tech. We've got a lot in transportation and energy as well. We're not really tied down to a single industry, much like HPCC isn't. We're actually going to be pretty broad across the entire spectrum of type of customers there. Now, one thing we do with all these customers, and actually just the market in general, is we do a lot of surveys. We send out information, whether they're customers or not our customers. Some of you may have gone to the survey. Some of you may have answered them. If you did, thank you. If not, why not? Just answer them. It's only a survey. But what we've identified is that there are a few things that every company needs, and they just don't know they need it. And so that's kind of what we're going to go over today. So one of the first things we found out was there's this failed promise of BI. You know, everyone is saying, hey, I need BI, I need BI, I need BI. It's going to be the next greatest thing in the world. And then they fail. Well, why are they failing? They realize that it takes too long. You know, they have to actually go through and build up this big, giant ETL structure, absorb the data, only to find out that the BI application also needs its own data warehouse. And that's something that we're aiming to change with our driver directly connecting to HPCC systems. Then they find out, okay, well, this is really, really hard to use. I can't put my developer in front of it. I can't really put a business person in front of it. It's just kind of this weird hybrid role. And so we aim to make that easier as well. And then there's a lot of people outside of context. So they hear kind of things like, oh, well, this is really cool. Let me go ahead and build this out. But they're not really in tune to what the end users actually need. They're not in tune to what their business users need or what types of business users they may have. And so they're kind of outside that context, and that's something that we need to identify quickly and work towards fixing. And then we also see that there's this unmet need. So we found that through our surveys, 93% of users say they want some sort of ad hoc ability. Right? They want to be able to query the data, generate their own reports, see everything they want to do, join the things together, and leverage that. But only 22% of customers actually have that capability. So why is that? Why don't they have that ability to actually see their ad hoc reports? And so that's something that we've kind of found out, and we very quickly found out that it's due to kind of some of the foresight of, well, how do we actually place these users into a use case that we can all build these items out of? And that's where we come up with this framework. The framework is what we call the continuum of self-service. So it's basically a continuum, as you can see. From the far left, you have the users that we call consumers. And those consumers are going to be, hey, I just want to see the data, maybe interact with it a little bit, and kind of personalize it and maybe use some filters. So this is what we usually see as our 80, 85%, 90% use case. And these can be anybody. So they can be workers on the floor. They can be managers. They can even be your CEO. These guys, again, just want to walk in, see all this information on their tablet, on their smartphone, on their computer, and take action based upon that information. All right, moving forward, moving into a little bit more of self-service capabilities, we get into our creators. Our creators, okay, they're, to be honest with you, a little bit more intelligent. They want to build out their own reports. They want to be the one to say, hey, I need this data, I need this data, I need these visualizations, I want to lay it out this way. And that's what we see with our creators. So now we're taking it from just viewing the data, maybe slightly interaction, to actually creating some use cases, authoring some information, and then perhaps even sharing it with other users. Can I share it with other people? Can I share it with people on my team? Can I share it with my CEO? Because these guys are the ones who are actually creating a lot of the reports. And then finally, we move into the analysts. All right, so analysts, they want to look at the data. They just want to explore the information. They may have no clue about what they really want to see. They just know that they want to have all the data in front of them and be able to find trends and identify, again, what's going on there. And so this is more of a self-directed. They collaborate with other users. They say, hey, look what I found. Isn't this trend interesting? And then they start having a collaboration right then and there. And so that's really what Logi Analytics is about. It's about presenting our data, your data, all that data that you've gone through and looked at your HPC systems, all the forecasting you've done, all the machine learning you've done, and present it to the end users in a very quick and easy way. There's not going to be any coding on the Logi Inf side. We'll be able to work with a lot of your ECL code, your web services, your stored procedures, and connect to Thor and Roxy as well. Now, the way that we do this is through a two-product approach. So first, again, if you think about the continuum of self-service, that's where these items are coming from. So from that defined experience, that consumer side, that managed experience is the creators, and then the self-directed, again, is the analyst. We've got Logi Info that's meant for the platform. This is a developer-focused application platform that will directly connect to a variety of data sources, including HPCC systems. Again, that can be your Thor, that can be Roxy, that can be your web services. We created a proprietary driver that we're using within our system. That way we can directly connect you to it. And this will give you the ability to create these managed reports, these defined experience reports, with a variety of different types of interactions for your users, tying in your different security models, tying in, if you want to embed it inside of your application, you can do that as well, and then making sure that it's useful for your end users. And then that spreads out through into a managed experience as well, and giving them the creator role. We have some flexibility there. And then you can see that there is going to be some overlap in the self-directed experience, the analyst role. And that's because, again, this is going to be from basically what we call the top down. We've been told to build this, so we're going to build it for all of our customers. Then on the other side, coming in from the other direction, from the analyst role, we have Logi Vision. Logi Vision is our discovery application. In this application, we go through, we connect to your data source, we bring it into a columnar data store, and then we allow you to rapidly define experience behind that, identify new trends, and interact with the data in a variety of different ways. And then as you go through there, as you identify new trends, you can start having that collaboration with Logi, with the different users, and these also both talk to each other. So if I want to deploy something from Logi Info into Vision, I can do that. If I want to go from Vision to Logi Info, I can do that as well. And that way we can tie in all your different models. And as we go through, we can even connect to the different data sources as needed. So one of the other things we've noticed is, again, the rise of embedded analytics. A lot of enterprises, a lot of software vendors, they have their own applications. They have their own portal. They have their own way of actually seeing the information. So because of that, from a user experience perspective, why don't we actually embed it inside of that portal or inside of your application? Earlier you saw a few applications that are having some good use of some BI items. They have their different charts in there that your end users were able to interact with. Now, instead of actually coding that and insert random JavaScript library here or the library that you might use, through Logi Info, we can have that and then some. So there's a little bit more power behind it. And again, it's all going to be natively connected to your HPCC system. So what we do is we figure out, well, why have to rebuild a data warehouse when you guys already dedicated time and effort in actually building it out, thinking it through? You have all your ECL code there. So why don't we just re-leverage all of that and have it stream into Logi? And that way we can have some real-time reporting. Whatever's in Roxy is whatever we'll display. There's no batch process for us to wait. Oh yeah, sorry, I know you did that yesterday morning, but we only do batches every week. So you don't have to do that anymore. If everything's all within the database that we're pointing to, we'll be able to report off of that. So the first thing I want to go into is Logi Info. Again, Logi Info is our platform product. We create basically a web application. At the end of the day, HTML5, JavaScript, CSS. No need for Silverlight, no need for anything special for older browsers, because we do deal with government. I'm from Washington, D.C. We deal with government all the time, and we'll downgrade the visualizations there. That way we can deal with those people who won't upgrade from Windows XP, unfortunately. So these items can also be scaled. So much like you would scale your HPCC systems, we can scale Logi Infos as a web application. So it can be horizontal or vertically scaled. And then things like Gartner, they can rate us as one of the higher embeddability applications that are available to you. Now, the way that we integrate with HPCC is, again, through a driver that we created. Now, many of you may recognize this slide with minor modification. And that's because we stole it from Flavio on his website. So we took what used to be just a generic kind of web application there, and we actually put Logi Info there. And because at the end of the day, again, Logi Info is a web application. Now, where we differentiate ourselves from the other BI applications, again, is our embeddability and the fact that we'll directly connect to all your different data sources. So we've been working with the likes of Arjuna and Flavio and Rodrigo for quite a bit of time now, and one thing that they said to us was, well, there's really not any native connectors to the BI applications, or they all want to absorb all the data into their data store. It'd be nice if I can harness the power of HPCC and present the data in a variety of different ways. And so my team took that and we're like, all right, well, let's see what we can do. And what we decided to do was actually to build out a native connector. So now we have a driver between HPCC and Logi Info that we're continuing on enhancing. And one of the hardest things to do with that driver is keeping up to pace with Rodrigo. I think every time I talk to him, he's like, oh, guess what we just added? And I was like, oh, now I have to go back and get the driver rewritten. But it is what it is, and it is something that we are aiming to do and to make sure that we can have that connection going back and forth. Again, Logi Info being a web application, what we'll leverage is a studio environment, which I'll be happy to demo to you as well. And that's our design environment. That's actually how we build out these reports or these dashboards or this information for your end users. And that's all going to be done through what we call an elemental design model, building block approach. But once you create that application, regardless of what kind of device you have, you can allow your users to actually see that data. So again, laptops, desktops, tablets, smartphones, we do a design once and deploy to all. And that way, HPCC is really at the harness of anybody, anywhere, at any time. And that's really what we all want at the end of the day, right? All right, so let's go ahead and go into a demo. And this will be a little difficult because I can't see what's on my screen here. I have to see what's on my screen behind me or down there. But that's OK. So here we have an application. And this application here, again, is built through Logi Info, leveraging HPCC. Now, all of this is actually running on my laptop, so I forgive you if it's a little bit on the slow side. But as you can see, there's a lot of different types of functionality we're able to provide to your end users. They can go through and start manipulating the filters. They can go through and start interacting with the information the way that you want them to. Again, this is for those consumers, the defined experience, picking and choosing what we want to see and how we want to see those. As they go through and they interact with the information, they can even look at and drill into even more data sets or different types of visualizations there. Now, in this case, you have one way of looking at it, but there's also other applications that we have that look totally different. So you can have it make sure, again, we're embeddable, so you can make sure it matches your application, your portal, the way that you want to. It could be a standalone application, or you can embed bits and pieces into your application. But regardless of how you do it, there's still a lot of functionality in determining, maybe if you look at the scatter plot on the bottom, my bottom left, you can see all that information there. And as we go through and zoom in, we can see even more information. Your bubbles can change colors based upon what they want to. So you can use some of that ECL code to actually generate the colors, and that way you can bring in the kind of a heat map type feel into the visualization. Or you can leverage Logi Info to do that. It's all up to you on how you want to present and leverage this kind of information there. We can go ahead and see other reports. So we can do forecasting. You can see a lot of information and interact with it in different ways. Well, we can go ahead and choose to exclude information. So passing in parameters into your Roxy, your Thor commands, and bringing it back information. All of that's available within Logi Info in presenting this information to your end users. And then for those that want to do geospatial type items, so whether it's geofencing or if you just want to map your users across the United States or London or UK, you can do that. And so, I guess the internet's a little slow here, but you can also bring in things like Google Maps. So integrated into the Logi Info platform, we do have a native connector to Google Maps, as well as a variety of other types of mapping sources. We can easily be extended, so if you do have your favorite JavaScript library that you want to leverage, we can leverage those as well. And so there's really a lot of flexibility there in the way that you want to present that information. Now, sometimes you may have real-time data that you want to stream across different values there, and so we'll have that flexibility as well. And in this case, here we have a dashboard that we've created, and there used to be a US weather map there in the bottom center, but I guess the internet's not working. But it's really no big deal. You can see all that information. We can feed it directly into Logi Info. So if you do want to do some real-time information, we can easily query out the information from all the different data sources that you may have. Again, totally different look and feel, and that was really our goal. We wanted to make sure it matches your application. That way, when you bring HPCC to your end users, they don't have a disjointed user experience. You want to make sure that their user experience, their user interactions all remain within the application, and they think that it's all a single application. And again, that's really our goal behind that. Now, okay, so how did I build out these items? How did I go through and generate these types of reports? Well, it's all done through Logi Info Studio, and that's right here. This is basically our design environment. You can think of it as an IDE, and some people do relate it to an IDE. But you can see that we have these little elements here, and these elements represent report components. So right now, you can see I have on this screen here, I have a div structure. Basically, hey, I want to lay some things out based on divisions. It's kind of like HTML when you want to lay things out, and we're easily able to generate those. But, all right, so what if I go ahead and want to actually build out a new application or a new report here? Well, we have our wizards, and our wizards allow us to easily create some new things. So let's say I want to create an analysis grid. So we're going to move into some of that creator type role, being able to actually build out those visualizations. Well, I can choose, for now, we're going to connect to Thor and Roxy, so that's kind of a SQL-based type item. We could write a little SQL interface for that. I can choose the connection that I want to connect to. Oops. All right, so it looks like I have a little item here. Let me go and double check some things. All right, so here you can see our different types of connections here that we're able to go through. And for some reason, the other one got deleted by accident, but that's all right. What we'll go ahead and do is run through, and what that wizard would have ended generating is this XML, or this structure here. Now, while I'm on this, these are our elements. This is what we had to build out these items. And as Flavia was saying, we used to be known as Logi XML, and that was a couple of years ago. And the main reason is because at the end of the day, what we're producing really is an XML document. So this actually will integrate easily with all your different types of source management control. So things like Git, Subversion, TFS, easily integrated into there. It's just a file system, so when as things change, you can still check and check out those items. We do have a built-in model as well. But what we'll end up getting here is what we call the analysis grid. And the analysis grid is a way to allow your end users to quickly create new visualizations. So as we go through here, as we build out these items, we're able to tie them together and then present that information, that data, to your end users. So as you can see here, here's a quick data table. That wizard would have taken care of all of this. And then from there, I can go ahead and start doing my own formulas, going through and actually filtering out the information right here and there, as well as going ahead and start creating my own visualizations. Now, there's quite a bit of data here, so we'll look at that information, and we'll be able to generate those items, and you can see really the types of visualizations that we're able to quickly create and choose how we want to present that information there. And then from here, we can add things out to our own dashboards and everything like that. Now, one of the other items that we have is going to be our Logi Vision application. And Logi Vision is, again, for our visual analytics, our data discovery application for the work group. And this is what enables your end users to quickly discover what's going on, connect to the data, pull the data back that they want to, and start interacting with it, joining it with other data sources, whether those be web applications or flat files, so CSV and XML documents. And so we're going to give you that capability and then let you go ahead and discover that information. So as I go back into the application here, oops. We'll go ahead and see Logi Vision. And again, Logi Vision is our discovery application. This is where we're going to go through and identify really what's going on within the information there. Let's see. So the first thing that we're going to do is we're going to log in. So it ties into a lot of the security models that we have that you have available. And once they log in, your user's going to have a notion of different projects, and those projects are basically data sets. They can be shared with a variety of users. They can be kept alone to themselves if you want them to. And so you're going to have a lot of flexibility there in how you want to decide it. So if you want more of a, one of your HPCC guys to go through, identify the data sets that you want to provide to them, and then provide it to them that way they're not able to actually pull data themselves, you can do that. Or if you just want to have them be able to actually do it themselves, you have that capability also. So as we go through this, we can see a variety of ones that have been shared with me. I'll go ahead and drill into that information. We'll pull up that data. And one of the first things we want to do is actually showcase the information. So a lot of your analysts come from an Excel background. Excel is probably one of the most widely used BI tools in the world. And that's because that's what everyone uses. It's very easy to use. So we're going to show you the data and let you interact with that. As we look through there, what we can actually see is a lot of information. If I want to start grouping these items, I can just say, hey, let's group it. And then we have a recommendation engine in the background that says, oh, thanks, you gave me a date field with 100,000 records, and I'm going to break it up by the year-month combination. And you can see that it did that automatically without me asking for it. If we want to override what we're looking at, we can definitely do that also. But if we also want to go ahead and say, well, let me go ahead and chart some trip durations over date. I wonder what that looks like. You can just do a drag and drop. And now the end users are actually building out their own visualizations. Again, the recommendation engine in the background saying, hey, you gave me a time series and a metric. So the best fit is a visualization, is a line chart. If I want to override that, I can easily do so and say, hey, give it to me in calendar, because maybe that's how I want to see this information. And so we can have it automatically overwrite that also. So all of this is being driven by your end users. We're going to say, hey, these are the best practices based upon all of our research with people like Stephen Few, who are visualization experts. And then based upon that, we're going to present that information. Now, as your end users actually see this information, they can send it to their info board. And their info board is a combination or a collection of different types of visualizations that have been created and shared with different users. So now they can see all of this. We're bringing in a lot of social media type aspects of, hey, let's go ahead and talk about this. And speaking of social media, Jithan, if you're working, go back to work, thank you. But you can see that we have a lot of information, and we're going to be bringing up more information, more important data to the front of the aspect of based on, hey, were these ranked? Were these comments? Who's actually interacting with it? Is it important to you, or is it important to everybody else? And we'll tie all of that together here. So if I want to go ahead and tag people, I can go ahead and look at the visualization and say, okay, well, I'm identifying some information here, and let me go ahead and tag people much like I would tag them inside of Twitter or Facebook or anything like that. I can just type in their name here, and now they have that kind of interaction. And so that's really Logi Vision. Again, it's more of a discovery application that we're presenting to the end users to help them identify what they want to see. And so as we go through this, if you have any questions, we actually set up a special email, lexusnexus@logianalytics.com. So that's going to be read by me and a few other of my colleagues who've been helping me work with Rodrigo and Flavio and Arjuna in actually getting this information. We do have some of our reports or research that we have available on self-service, on embedding analytics, all available online. So if you want to check it out, please do. And with that, I appreciate your guys' time. Are there any questions, even though there's not much time?
So just to really geek out, Donald Norman and his interface and the gulf of uncertainties between users and Okay, so I'm just trying to work out, like, what's the underlying calculus of visualizations? Like, you know, I don't even know how to ask my question. You know, that's how undefined it is for me. But do you have any idea what I'm talking about?
I can do my best. Unfortunately, I'm not psychic, but when it comes to visualization, it's all about making sure the visualization is clear to the end user, that they know exactly what they're looking at based upon what you're presenting to them. If I have to think about it for more than a minute to figure out what am I actually being shown or what am I looking at, it's probably not the best visualization. So there's a longer answer for that, and it's go buy a textbook from Stephen Few, and it's about 4,000 or 5,000 pages. Have fun. But he's kind of one of the foremost experts in the visualization arena. And so we kind of abide by his stuff that we kind of go when we go through and identify what kind of visualizations we want for our recommendation engine. Was there another question?
Yes. How do you avoid Roxy queries and Roxy indexes getting out of hand, especially in a discovery kind of scenario? The permutations and combinations of the dimensions could be like endless. Mm-hmm. And I'm assuming this is all being served by Roxy on the back end. And there is a fundamental problem there I see of just managing the indexes to support all those permutations and combinations.
Yeah, and so that's kind of a standard database technique, and it's identifying really the more important indexes that you want to filter on and present to the information. So you're right, Logi Info does work directly against things like Roxy and Thor, and so it's really going to be more of a, for lack of a better term, a DBA type exercise in determining what really you want to present to the end user. Unfortunately, I'm still kind of trying to think about how I present that and how I'd work with that, and there's a lot of different combinations that we can leverage. But it's probably more so identifying the most important index or a group of indexes that you actually need. All right.
Very good. Thank you very much. It was a great presentation.
Thank you.
Great. Thank you. Very good. We got off to a great start for this block. By the way, Rohit, on that question, I just want to add one more tidbit, which is there are ways to handle indexless queries in real time in Roxy, particularly using capabilities that we built in Salt called score search. Nothing is completely free. This requires that your data fits in RAM across the Roxy cluster, but it works without indices, so you avoid the combinatorial number of indices that you would need otherwise. And you can still do slicing and dicing in real time, grouping and essentially scoring linear models.
So with the same sub-second response?
That is sub-second response, yes. Yeah. So score search from Salt is a good capability. Very good. Now, off to our next speaker, and this will be Mike Young with Infosys. He has a great case, and you will see it, about a company which is one of the largest appliance manufacturers in the world, particularly in China. The name of the company is Higher, but Higher, not Higher. Anyway, that was a bad joke. So, Mike, the stage is all yours.
Good morning, ladies and gentlemen. So I'm really glad to have this chance to share our experience with all of you. A lot of story actually, because this is a huge project we done for Hire. So first, let's myself the introduction. Myself come from Shanghai. Actually, the 16 hours flight I go here. I'm the principal architect in the Infosys. I already been in Infosys around 5 years. So before that, I have worked on the Google and the eBay. So that's majorly in e-commerce company. So actually, I meet the Flavia around 2.5 years before. Then after half year, I make a crazy decision. It's introduce the HPCC platform to our key customer. And also, I'm not sure how many people know the Infosys. Actually, Infosys have a very good the video to introduce. But for myself, I just want to have the draft concept to you. The first Infosys is a typical production mutual company. So actually, Infosys done a lot of research on some commercial products, and also we have the golden partnership with Oracle, with IBM, with Microsoft. Now we also have with the LexisNexis, but also Infosys. We do a lot of deep research on the open source. Actually, before I met the Flavia, that time I have a lot of projects on the big data. Mostly we use Hadoop and Spark. I have a huge team on this area also. After the talk with Flavio, because I'm technical fans, so then just in the night I downloaded the HPCC and try to see what's the magic happening inside. So the crazy thing is almost just 2 days, I can write the simple ECR language, and then to check the result. I feel this is a really, really good system. That's the reason I made this crazy decision to introduce this platform to hire. So secondly, the Infosys actually our the philosophy, the building tomorrow enterprise. So how to help our customer to build a tomorrow enterprise. We measure the 2 areas. First area is we will do a lot of research on the different platforms, compare them each other, think about, okay, which is the better. Of course, we not just balance the technical, we also will balance the business, the cost, the schedule. On the right hand, we will do the deep understanding for our customer, their business. What's the challenge at the meeting? Then we'll think about, okay, now at this time for this deal, so we will merge it together. So hire, it's come back to the hire actually. This is a large background in the China what's happening. I think all the people might know the Alibaba, and just go to the Nasdaq, very famous. But this is just one snapshot. In China, we also have Tencent, Jingdong.com, and more the e-commerce online kind of company is doing really good business. But in the online company, they have a really good design to capture user and to understanding and insight user, and also have a good mechanism on the back end to think about how to influence user. So this e-commerce company, what's the typical is working. But in China, it's not like US. US e-commerce company or e-commerce service is just a good complement for the offline business. But in China, it's a total difference. In China, actually, the online business really give high pressure to traditional company, really high pressure. So retail company is the first they get this high pressure. Now is the banking, insurance, telecom company. They all have the big pressure on this. So whatever the company itself, or the China company, big company, or the government, they are using a concept that we call it Internet Plus. So Internet Plus, the meaning is plus. That means all the traditional company. That means all the traditional company you need go to internet. So this is a big topic for all the famous company in China. But for the traditional company, they're really poor on this area. It's not like e-commerce company. E-commerce company know very much how to capture customer, how to insight the customer, even how to influence customer. I give an example like in Amazon or eBay. I give a good the recommend system. They have on the back end, they can recommend some good things for you. But for a traditional company, they're difficult to do that. because mostly their online is very poor, offline is very huge, but in the offline they are difficult to get information, collaboration the information, even to insert the information for them. This is very difficult for them. This is a business challenge. For the traditional company, another challenge is on the technical side. China, the e-commerce company, when they just start, they major leverage the IBM, Oracle, those kind of production. It's very popular. It can see huge the Oracle cluster, even for Alibaba. But around the 7 years and 8 years before, they start to gradually remove those production. Around the 3 years before, like Alibaba, they already zero Oracle production. EIX, no. So all is cluster-based. So, they done the huge research on this area to smoothly their business, their website. But for the traditional company, they are not IT company, so they cannot put so much effort and cost on this area. So they also meet the bigger challenge. It's how to resolve this problem, because use Oracle, IBM, definitely the cost is very high. But for them, this is a must to do that. Otherwise, how do they do the e-commerce? So this is also the huge challenge. So on this background, so for the hire, what he want to do is, can you help us use the Trapest low cost, especially on the license and the hardware? Also help me to try to capture user, insight user, and even tell me how to influence user, use the social media, or give a better service to their end user. So this is a big high-level topic for this engagement. So, when we started this engage, a lot of challenges in our front. So I just give a few very hot, first the real-time transaction. When I think about the HPCC, that time I'm very familiar, is HPCC can do the backend, batch kind of the work, analytics work is good. But the real-time, I needed to figure out how to handle. And also the problem is, for the customer, they are very business-oriented. They are not very ideal for the backend technology. What's the batch job? What's the real-time processing? They don't know. They said you are big that you can do everything. So this is the one big challenge. Second big challenge is for data consolidation. Data consolidation is very tough things for the traditional company, because like here, the inside they have more than 400 systems. Even for some data, same data, you can see the same records on a different system, but use different attributes. So this data consolidation, the big challenge for us, we finally found that we put a lot of effort on this area is after you process the data, clean the data, create one single view for the customer, but you still need to verify with original system. For example, like you have A system, B system, they all have the same data. Then finally put into create one data, you still need to think about how to compare with original system. So this is on the HPC, when we use HPCC, we do a lot of additional compare job on the back end to think about on each stage, the data, whether it's a match with original data. So this is also a big challenge. Thirdly, regarding master data quality. Actually, this word might not be very exact, because master data is answering one thing is you are exactly you. No duplicate records, and for one record, no confusing data. This is master data is answering. But on the big data area, that means your behavior is exactly what's your behavior, and your data is exactly your data. So that means apart from some master data, we also need to handle a lot of transaction data. And then we need to do a lot of merge work, consolidation work, even dedupe work. So this is also a big challenge. Thirdly, the warehouse report. Actually, it's impossible for us. We have a big data platform, and also we have a warehouse system like Oracle OBIE. So when I do that, when I started this project, actually I not decided. But finally we find HPCC is really powerful in this area to help us create a report. Then the last one is unstructured data, the data mining. So I will cover this on the later more detail. So these are our challenges when we started this project. That we know this challenge, so that's the reason I see this a crazy decision. So when we started this project, to frankly give a best option to our customer, we do huge comparison. Ourselves do that. We do not to reference some documents. We ourselves to manually to do that, to think about, okay, on the different metrics, HPCC and Hadoop, we should HPCC or Hadoop. Finally, the key dimension make this, I decided to HPCC is measure the first on reliability. We have a lot of projects that use Hadoop and Spark. Actually, we find not much, but you can see sometimes it will happen. The data reliability have a problem. Some is because the open source module have a problem. You need to have the latest version. Some is a problem is you find it's some file system problem, but you cannot realize. So we find this is a really disaster for us. But HPCC I didn't find. It's robust on this area. Secondly, regarding the productivity. For myself, I almost use 2 days can write the single logic, but almost use 1 week, 2 weeks, already can run very complex the query to try this. So this is very impressive for me, because even I have a big team on the Hadoop and Spark, but I still, our customer in Qingdao, but we are in Shanghai. So that means it's impossible. I have my Shanghai people long-term working in the Qingdao, so I need to ramp up the Qingdao people. So I'm saying this is very important for productivity, how easy to learn, how can quickly create the logic. So these two metrics is the major reason I get a final decision. But for our customer, they also is asking me you are writing whether you really wanted to introduce HPCC to us. So, but of course, finally, I convinced them. But they are business people. They are not know the technical detail. But they still have a lot of questions. I give example. They also is a concern for the training. I said, how long my people can handle your system? So, but finally, let's prove this is the right decision. So this is the. So these are all the metrics. These 2 metrics are the most important for me. So this is another interesting challenge. Our customer, most people that do not have the IT background, even not the computer science, the major. So for them, they have a lot of demand is, okay, after you roll out to the production, after it's in the real time, if I need to change something, please don't tell me I need to change the code. I always need a runtime support, and also I just drag and put my query or my condition or some sets operation like a difference, like the unify, those kind, then I can do that. It can work. So we on the front end, we use the Java to create all the UI, let them take a drag and combine and even merge. Then on the back end, it automatically create ECR, the language can run. We do the same job for use the Hadoop, but it's really cannot imagine it. It's we use really less effort to support this function. So this is very impressive for me, and I appreciate it for the HPCC. This is another very important feature for our production. This might be the Chinese, but I just see it's first is have the user basic information like a phone, like the address, like your birthday, and also you have all the transaction data like what you already bought, what you complained, whether you complained on some time, what's the service you asked, what's the production quality you escalate, and also we have all the communication history in WeChat channel or the QQ channel or online channel. So we put them all together to create one single view for the customer. Apart from that, that's the raw data. Apart from that, we also use some data mining to create some label. So this label, like I give example, like you are high value customer. You know what's the high value? You have a lot of condition you need to think about. Then to find, okay, these people classified should be done beyond the high value customer. Then after running that, we have labeled this, okay, this person is a high value customer. So we put it together, have a single view. So this is the first, this is the challenge. Second challenge, you know, they have almost 220 million end user data, history data, and it's more than 10 years data. But you know, they need less 1 second to find any person. This is search capability. And also, their search condition is very complex. Like any dimension, any attributes, you can search the people. I give example, you can, based on the production series number, you can find, okay, who buys this production. So, you know, this is a big challenge for HPCC. Because HPCC, you want to search, you must create an index. That means you need to create a huge index. The speed, if you copy from the SAW to the Roxy, all the index, just the copy index, is need a long time. So, but we use some, finally we use some cache to cache some index to how to go around. Of course, I think Flavia, you also think about in future if do like the Google kind of work, how it can work. So this is a search kind of capability. Third is, you know, all those data that need a service at any channel, any time, and any of the data, and also have a correct authorization, the security control. So that means all the data need to publish at the service. Also, you need to do a right filter for same data. Then we'll filter right data, go outside. So in this project, we measure count on the Java to do the security control on the front end to control the security. Then deliver the data to the right the channel. So this is the on this function, we put a lot of effort to think about, okay, how to make it enable. Last one also is the most complex thing for challenge for us. Is this map need support real time. That means that we cannot fully count on the HPCC to fulfill the data. So our final solution is we create a cache cluster and partition the cluster, the cache then we, for the final result, we will merge both data from HPCC and the cache and create one single view to the customer. So recently, I talked with Arjuna. Arjuna recently is also started thinking about the real-time support for the HPCC. That will be really good. So this is another interesting thing. You know, in China, currently, all the traditional companies, they're very careful. They're very careful for what the people are talking about for this logo, their branding, and what they are talking about when they're chatting with their service people. Even on the back end, the research, the R&D people, they also would like to know, okay, firsthand the feedback from the public sentiment, and then give them. So this is all needed to handle the unstructured data, very exactly to handle the unstructured data. You know, before this project, for this purpose, so they are using, because every day they have almost the 40 million, 400,000 raw data, unstructured raw data. They are manually do that. So almost they have the 20 people every day just work on that. What they do is they want to classify, okay, what's the positive, what's the negative. This is talking about the production problem. This is talking about the service problem. This is talking about the logistic problem. So every day do that. So, but our project is try to automate everything for what they already done. So, for the Chinese is actually very complex than the English, because English by nature, the space is nature. Other words is exactly word. But the Chinese, if you will have the four words, you can, the 2 words and the 2 words is one meaning. You also can have 4 words, one meaning. So that means it's very complex. Also, the grammar is a difference. English grammar is more easy to do understanding, but the Chinese grammar is very flexible. So to hit our target, so we need to use first the Chinese word segmentation. So we need to set up a very good quality library for our customer. Second, we use the deep learning, the word vector. So we use the word vector to try to automate it to find the right keywords for our future the learning. Thirdly, we use the paragraph vector. So that can help us automate it to do. So finally, accuracy is really ideal. This is almost 90. So this is also good. This is the Filippo Cotolo. So I'm the fan for Filippo Cotolo. I read a lot of books. So he is a guru for the marketing area. So here he had one subject is good company should focus on the right target market, and they will try best to find the right target market and give the good delivery for those market. He also defined a different dimension to help you analyze the people. So in our project, we based on available data, based on his theory, to think about, okay, how to do such customer segmentation and how to create a business value and give a better recommend for their business. So I will not extend for all the detail, but one major is, for the geography. We need to find, we have one scenario, it's, they have a huge offline service people. So any offline store, they want to use our system to find, okay, surrounding him, around 10 kilometers, who is the company for hire. So this is just an example how we use HPCC and use segmentation to find the right person. So this is also the big sense. This is the surprise actually for me. First is we find, when we use Hadoop and Spark, mostly when we to create a report, we will export all the results to the database. Then in the database, use some existing tools to drag out the report. But in the HPCC, it's very easier because it's published in the Roxy. You also have the service, and even you can put more parameter than the Hive or than SQL to create another report. This is very flexible. Second is ideally the master data. Of course, not just master data, it's all even included the transaction data. Last one is we feel it's do the warehouse job is fully can do. Because in the Oracle, if you want to do the warehouse, you need a physical architect, logical architect, and a business architect. Otherwise, the performance have a problem, right? So, but in the HPCC, it's all not required. You just put through the data inside and write ECL, then everything can work. If not work, you add one machine, it's better. So this is very impressive. This is one technology matrix. Actually, if you see, this is a huge project. HPC as a core part on the data store and analytics. And we largely use the cache, and also we largely use some SOA service at the SaaS layer. And also we do a lot of integration with third-party system and some other, like cache and SAW, how to sync up the data. So we do a lot of job on how to improve the performance at the same time to handle the final result. So, but this is also the golden learn for us, and we also give some good feedback to our HPCC, the team, tell them, okay, what's the challenge we are facing. like the real time, this Arjuna really give a lot of good idea. So, this is the matrix. So first is I really want to thank this chance is Richard Taylor. They really give us a good help. He go to the Qingdao and give us training. Really thanks. Secondly, I wanted to thank the Jill. Jill give us a lot of online and offline technical support. Very quickly give us support. And Arjuna, Flavia, really give us a strong support. This we are really appreciate. And as myself, because my major focus on Asia, I still keep learning do the deep research for the HPCC. Currently, a major area is I'm thinking, is it possible HPCC to replace SAS or Teradata? You know, in China, a lot of companies that want to do things, traditionally they will use the Teradata and the SAS to resolve, but they cannot afford the cost, the license cost. So I always do a lot of research and think, okay, is it possible? If it's possible, then how to do that, what cannot do, what can do. So this also is my honor and pleasure if I can introduce HPC to more of our customer in the different industry. So this is good. This tool is this platform is really good. I highly appreciate it. Thank you. So any question?
In your customer 360-degree view of an individual, did you use just the data from Hire to link people and behaviors, or did you use other data outside of Hire?
We also have external data. That's major from like Alibaba, Taobao.com or Jingdong.com. If we can have the link to this person, then we will link this information inside. So we also have the external data. Hi, Michael.
Actually, Arjuna suggests me ask you in Chinese, but well, actually, we found something very interesting. Both you and the CPO online, I forgot, it's David, is that right? You guys said 60% productivity by using the HPCC compared to some other ones. I'm very interested. You guys probably do your own matrix, but you come with the same result. I just wonder how you measure that productivity. Maybe David, you can share as well to see how we can, how you guys come up with that.
Okay, so actually, you know, we train a lot of people. Before HPCC, we train a lot of people on the Hadoop side. But when we have HPCC, we also train the people. So you know, before the HPCC, when we have one people, he might the computer science is just a graduate, but don't know too much circle. If he want, before he can write the code and can have some business output, we mostly need 2 months. 2 months. Because you know the Hadoop and even Spark, it's a zoo. You need to understand a lot of module before you can create some result. But for the HPCC, most of the people, they can finish almost in 1 month. And they even either use 1 week and 2 weeks, they can write very simple the language and give the output. Other things, he will not worry so much. And also, a lot of like ECL, the watch, this higher price Richard, so the watch can help him to monitor those kind of what's going on. So that's the reason I feel that at least on productivity, it's double than the Hadoop and the Spark.
Yeah, hi. Basically, our operations team monitored the throughput of all the jobs. So when we get a typical request for reports or analysis, we spend a lot of time sort of looking at how long it would take to produce those data sets, and we could basically aggregate that analysis over a long period of time. And what we noticed is literally that time difference to produce actually not even the same report, but something actually much, much better, and 40% of the time, basically. So what we were finding is we were all geared up to hire a whole bunch of new staff, and we just said, look, we can cope with the client's needs with that current amount. I mean, we might well increase it in the future, but that's just because the business is growing, not because we can't cope or that technology. But literally, our ops team said, look, we can cope with this many people doing this amount of work. Okay.
And also, one thing I just compliment, when I to use Hadoop and Spark, we most of the work we use a Hive, but the Hive, the function, even not so powerful as SQL. And it's less than SQL capability. So a lot of a scenario, we are obliged to write MapReduce Java the code to manually create some special function. I'll give an example like mapping, normalization, denormalization, even some dedupe. We need to write our customized function for Hadoop. For Spark also, we use the Scala to enrich the MLab library. But in the HPCC, at least in higher, we customize the function. So this is improve is huge. It's improve is huge. So really appreciate. Okay, thank you.
Thank you, Mike. This is great.
Thank you.
Thank you very much. Thank you. This was very good. I'm already energized on these two talks. This is a great, taking a project like that from zero to getting it in production in a very short period of time for a very large customer, which is a reference account for Infosys in China. I think it's a great achievement. So it's impressive to see the things, even though we know the capabilities that HPCC has, seeing them applied in a real world scenario to do this type of analysis is very impressive. Now, for our next talk, and by the way, those that are online seeing our live stream, remember to send your comments on Twitter. Hashtag is HPCC Summit. So remember that, please send us your comments. We are looking for them. For our next speaker, I want to put some perspective here. All of you probably think that you are dedicated because you woke up this morning at 6 or 6:30 to be here at 7. And some of you might have ranted, but you didn't say anything, which is a good thing. But you got here at 7 or 7:30 to start very early. But I'll tell you that's not dedication. I'll tell you what dedication looks like. If you married on Saturday, this just last Saturday, and ran out of your honeymoon to come to give a talk here, that would be dedication, and that's exactly what JT has done. JT, absolutely, he is right there. So JT is with IBM. He works on the OpenPOWER platform, and he has been the person who ported HPCC to the OpenPOWER platform. So I think that has a lot of merit in itself. And he will be here with Allan Cantle. He's from a company called Nallatech. Allan might be only one of the few people that can, probably in this room, code in. How many of you can or ever coded in VHDL or Verilog? FPGAs? 1, 2, 3. Well, and Allan. Very good. So please help me welcome JT and Allan to the stage.
Yeah, thanks, Flavio, for the introduction there. I figured it's only fitting that since we did our dry run when I was in my truck with my best man driving me to my bachelor party to come here on the honeymoon. But yeah, Allan and I are real happy to be here today. We got started with this with LexisNexis and HPCC earlier this year. Nallatech engaged with Flavio and about trying to get better performance out of Thor and Roxy clusters doing acceleration with FPGAs. Allan quickly got involved and he started looking at it and figured out that one of the big things that would probably help was porting to Power and OpenPOWER and taking advantage of our processor technology paired with the OpenPOWER infrastructure. So today what I want to talk about, we're kind of switching gears a little bit, getting to a hardware conversation, looking at ECL down. And so first I want to give a little introduction about the OpenPOWER, talking about why Allan and I are here on the stage together. Just give a little information about the actual port itself, and then talk about Power 8, give a little bit of background about how the key technologies in the Power 8 processor and how that can feed what we view to be a path to higher performance in using FPGA acceleration. I'll hand that over to Allan. He'll go into those details. So the OpenPOWER story, from a hardware perspective, in the 90s and early 2000s, hardware designers were really leveraging technology improvements. We get a new generation of silicon, and we map our design to the next generation of silicon, and we see a 2x performance increase. Moore's law, where double the transistor count, it really kind of measured, and we got 2x performance growth. Well, that started dying off probably 10 to 15 years ago. And so hardware vendors have been using different methods to still get that 2x performance that customers expect. And so at IBM, what we've done is we've integrated across, we're a system company, so we've integrated across the system to drive value at a system level. And we've done pretty well in that over the years, but then we looked at the industry, and there's a lot of great players in the industry doing very smart work in the I/O domains and the system domain. And we said, well, we want to figure out a way to better collaborate and work with them. So we kind of changed gears where, our biggest competition is Intel, and they're a chip company. They're not a system company. So they've been taking all of these great innovations like FPGA computing, recently acquired Altera, putting FPGAs on their chips. They've got GPUs on their chips. They've got networking on their chips in their socket, and they're kind of pulling things into the chip. What we're doing is we're figuring out a way to open up the entire system to let other very savvy vendors like Nallatech, NVIDIA, Mellanox, et cetera, system companies, software stack, to open up our infrastructure, open up our architecture, and allow the industry to come together as a community and deliver value to the customer. So about 2 years ago, OpenPOWER was formed with 5 founding members: IBM, Google, Mellanox, NVIDIA. I'm sorry, not Mellanox. Yes, Mellanox and NVIDIA. I think Tyan was in there pretty quickly too. And Nallatech joined very quickly. And in this last 2 years, we've grown from 5 to it's over 150 now, I think. So we've seen a lot of growth in all kinds of different areas. We're integrating at the chip level with companies in China they're going to make the next power processor, which is pretty interesting, all the way up through research companies and system stack type areas. So this is really what IBM is trying to do, is to match open source software and provide an open hardware technology to go along with that, so we compare those two together. So the port, a little bit of background here. The port was exceptionally easy, and a big part of that is because of the way HPC systems is set up. With ECL being platform agnostic, we can change the hardware architecture out from underneath you, and it has no impact to you, which is great. That makes it really easy to do that. And then additionally, the open source framework, the way things are set up using common build tools like CMake, GCC, BinUtils, Node.js, et cetera, that makes a rapid transition to other architectures as well. Open source is very key here because a lot of times when we work with customers trying to get them to port to our new architecture, you have a lot of difficulties getting source code and taking a look. They don't want to share their code, et cetera. But with HPCC being open source, I just went and downloaded it, right? It was real easy, and we can go look at the source code. We can poke here and there, et cetera. So we pair that with Power 8. We've we've been, in the Linux space for a while now, but with Power 8, we really kind of turned things around. We went to Little Endian, which was huge, because x86 runs Little Endian, and to port to Power in the past, you had to be conscious of how you stored the data. By going to a full Little Endian support, that's no longer an issue. So that makes things a lot easier. And then we've really done a lot of work in our software development kit to have our advanced tool chain for optimized libraries, doing post-link optimization, and then performance analysis tools. And also, we launched Power 8 with full support for Ubuntu. Since we've grown to support for Red Hat and SUSE as well. The port itself, it took less than a week. I don't know what the calendar time was, but in hours, it was very simple. All we had to do was go in, add some architecture defines for the new architecture, create this stack descriptor for Power, and then just use bin utils, which was very easy. Those were the 3 changes to get it to compile. And I'm a hardware guy. I don't know really much about software, and I was able to do it myself. So that kind of speaks to how easy it was. Kudos to the team for doing such a great job setting up your infrastructure. The port went pretty quick, but the deployment took a little bit longer. There were a couple of bugs found. Two of the bigger bugs were just because I was on a newer version of Ubuntu that had had a newer compiler and some changes to the init system. There was one with some alignment operations as we went to the new architecture, kind of exposed a bug with some of the atomic stuff. And a big part of it, like I was the monkey on the keyboard, right? So I had to take off my hardware hat and put on a software hat and learn how to look at the code. It went very smooth. The basic setup was really easy. Flavio asked me to say, what were the challenges that I had, and the biggest challenge that I had was, HPCC is set up to provide a framework for you to write ECL code. But for me, I'm a hardware guy, and I want to get under the covers. So it was a little bit harder to understand how to do kind of system configuration type stuff. Maybe some more documentation for some of those things would be great, how to look at memory usage, thread support, et cetera. So let's take a look at Power 8. So the OpenPOWER initiative is great to innovate across the system, but you really have to have a strong CPU to take advantage of system-level optimizations. I don't want to bore you with too many hardware details, so I've highlighted the things that are really kind of key for this environment, for this big data workload. We really are designed for big data. We've got up to 12 cores per socket at SMT8, so that gives you 96 hardware threads per socket. To feed that, we support up to 1 terabyte of memory per socket at 230 gigabytes per second. So that's quite a bit of speed there. We have some things in our architecture, new in Power 8, transactional memory, which helps when you have all those cores and you have contention over data. The parallel processing paradigm. Transactional memory should help with some of that, the atomic overhead, et cetera. And then to feed the processor, this is big data. You guys are talking petabytes, exabytes, whatever of data. You got to be able to get data in there. Sorry for the typo there, but we've got 48 lanes of PCIe Gen 3 capabilities per socket. So that's quite a bit of data bandwidth coming in to feed the beast. And then a new thing that in Power 8 that came out is CAPI. I'm actually the CAPI enablement team lead, and so this is close to home for me. But what we've done is we've taken industry standard PCIe technology and put a little twist on top of it. And we do this, any PCIe device you can attach with CAPI. You could build an ASIC that has some of the CAPI capabilities, but what we've kind of keyed on lately has been FPGA acceleration. This is a trend that's been in the industry for, Allan's been doing it for 20 years, and people have been really pulling this into the enterprise class servers. And we've just added a little bit to it. We've taken FPGA acceleration and given it the ability to be coherent, which is huge. Because there's lots of advantages for that, some performance, and one of the biggest is ease of programming, ease of taking these acceleration plays and pulling them into your application, you can treat the FPGA as a peer processor, you know, a hollow core, somebody calls it. So that's a very key invention for some of the work that we're going to be doing here. I list the advantages. You see the I/O model flow there with the traditional PCIe stack. There's lots of device driver overhead to get the FPGA or PCIe device kicked off. With CAPI, it's real easy. It's a shared memory model, so you basically have the application tell it to go, and it goes, and you talk directly with the application running on the accelerator. And it also opens up the ability to do some workloads that you couldn't normally do with PCIe traffic. Similar to like RDMA, but a little bit easier. So there's many CAPI products out there, but one that we find key for this area is our CAPI Flash implementation. So what we've done, we looked at our CAPI Flash Flash attach architecture, and you can see on the left-hand side there, that's the typical stack to get a flash drawer connected to your processor. And then on the right-hand side, you see with CAPI, you significantly reduce the programming stack there. So the number there, 20,000 instructions to get in and out of a flash drive reduces down to a couple thousand. So that has, you know, there's lots of benefits to that. One is code path. You reduce code path, you're going to increase performance. And also the ability to free up your cores to do the work that you want to do. Rather than managing your I/O devices for you, your hard, you know, your storage for you, you free up your cores to do the real work that needs to be done. So this is a kind of a pictorial thing here. On the left-hand side on the bottom there, we've got a 2U IBM S822L. That's a 2-socket server. You know, up to 24 cores, up to 2 terabytes of memory, et cetera. And then on the top, we have a IBM Flash Systems drawer, and those you can get those up to 56 terabytes of data in a flash drawer there. And we did experiments hooking up the flash drawer with the traditional conventional I/O fiber channel, and then CAPI attached. And what you see is because of the reduced, two things happen there. One, the reduced code length path getting in and out of the device. You see a performance improvement there. And additionally, there's some offload, some CPU offload of the file system onto the FPGA. So what that results in is a 5x better IOPS, input-output transactions per second, per hardware thread, and a reduced code latency. So what this has done is it's taking Flash, which is typically looked at as fast storage, and we've kind of changed the paradigm, and we're starting to make Flash look like slower memory. So with that, I'm going to hand over to Allan. He's going to talk about some future direction stuff.
Thanks, JT. So I'm going to just go into a little bit more detail on what IBM has been doing with the data-centric architectural approach. I'm going to try and explain what we mean by moving from this processor-centric to data-centric, and show you some of the complications that exist today in more traditional server architectures. I'm also going to talk a little bit more about FPGA acceleration, very high level. So first of all, a question: how many of you are familiar with FPGAs for compute acceleration? Okay, only a few. So I guess that. Unfortunately, I don't have time for a complete lesson in FPGAs, but they're a special type of processor, and I've got a fairly simplistic graph which will hopefully paint a basic picture for you to get the grasp of why these devices and GPUs are being used to complement microprocessors in different workload areas. So just a quick bit about Nallatech. We've been in the area of FPGA acceleration for over 20 years. This isn't new. I think Flavio might have mentioned, basically there is a low-level language called VHDL and Verilog for programming these devices. It's really hard to program these devices. So the people with strong hearts over the years have gone through the pain of the acceleration where they really need it, but it really hasn't made it to the mainstream. But now it's really beginning to make some serious traction, and it's got some very strong benefits for the world of big data, data analytics. Nallatech's been working it for 20 years. We work with two, the actual chip vendors are Altera and Xilinx are the two biggest chip vendors. And we've been collaborating with IBM on OpenPOWER. That's been tremendous, being able to get in at the heart of these architectures and help influence the changes. Our expertise is demonstrated. We're actually in production with IBM's System Z mainframe platform, so our products are embedded in there, and we've delivered a number of 1,000-node clusters with FPGAs. So this isn't really that new, guys. So it's and hopefully you'll be able to leverage it yourselves. So looking at the motivation for heterogeneous computing and using different processor types, you know, JT talked about the power wall, the hitting the power wall, Moore's law not scaling. But back in 1998, DARPA did a study, and they defined the perfect processor being a polymorphic processor, polymorphic computing. And this graph just shows you the ideal efficiency, swept efficiency they called it, size, weight, energy, performance in time for how quickly you want something to operate, or for your particular problem. And then they talked about data types across the x-axis. And what they did is they actually plotted a processor and, well, ideally the polymorphic processor would be equally good at all data types for all problem sets. But an early version, they actually plotted the microprocessor and an FPGA on it. And I've taken a bit of artistic license to cut to the chase here of showing where we're really at today. The key point I want you to take away is the FPGA processors on the side. You can see they're the best at bit-level processing and stream processing, two areas which are particularly important in the big data area. Microprocessors, multi-core, very good at the complex symbolic type data operations in vector, and the GPUs are really leading the field in the SIMD area. So using all three types of processors, you can actually get to the most efficient compute solution for your problem. So just restating, and FPGAs today are software accessible, which I'll just cover in a moment. But just to restate, FPGAs are best in the pipe stream computing. We've got a lot of data moving around. We build compute engines around the data. That's extremely efficient. And we're highly parallel for bit and byte level computation, which you guys do an awful lot of. So, but now, the big step change, which is really making a much broader adoption, is that they're programmable. They're programmable with a language called OpenCL. Is everybody, hands up, everyone is aware of OpenCL? Okay, not as many as I thought there would. So that was a language that was really invented with the GPUs. Apple started it, and it's actually buried in your Mac OS X. You can use it. It's a part of the OS with Apple. But basically, it's been adopted by all the CPU players, IBM, Intel support it, and all of the FPGA players. So you've got it's a low-level, explicitly parallel language that you can use to program all of these devices. So that brings a good bit of benefit. The other thing is because it's being adopted as a heterogeneous language of choice, it is developing in the working group to support heterogeneous computing even more. So switching gears to, Flavio kindly gave me a basic background of a 4 and Roxy cluster and a node. This is just showing the typical node configuration of the memory that's attached and the storage attached. The fundamental difference between a basic 4 and Roxy node is that Roxy uses SSDs. You get more improved bandwidth, and you get tremendously improved IOP functions with Roxy. I've also shown the green arrows are showing what was effectively the memory bus of the architecture, and the I/O bus, the PCI I/O bus, is shown in yellow, and you'll see the network and the storage is attached to the I/O. So, and as a cluster, just showing the complete clusters, on the left is the 4 cluster, and it's a bit smaller. I'm not sure if you can read the writing there, but on CPU-intensive operations on fragmented data, you've got an awful lot of network traffic over this 1 gigabyte per second. So that's really the weakest link in your CPU-intensive on fragmented data. On the mapper-type parallel functions, you've got a tremendous amount of aggregate bandwidth, 160 gigabytes per second, 56K IOPS. With Roxy, because you've got good indexed, you've got good indexation. That means that you can get over some of the network issues, and you have greatly improved IOPS to your storage. So, but let's take a closer look at memory coherency and data movement conflict. When you actually let's take a look at a mapper type needle in a haystack operation, where you've got really little to no compute going on lots and lots of data. On a current processor-centric architecture, you'll see that we've got 1 to 100. The memory bandwidth is 100 times the I/O bandwidth. So this is fairly forgiving of this type of architecture. So it's not a problem for the Xeon, so why do we need to worry about it? Well, let's just take a closer look. The burden of using a CPU-centric architecture for data-centric problems is that data from the storage goes into memory, goes through all the caches, does a simple operation, and if there's a result that comes out of that, it'll then goes back through all the memory layers back into that storage. An awful lot of data movement for such a trivial operation. And so it really does, although the Xeon can cope with it very easily, it creates a lot of unnecessary traffic congestion on the I/O. I/O management consumes CPU threads, excessive cache thrashing. Only 8 4K IOPS fills up a level 1 32K cache. So you get really tremendous power and efficiency issues with all of this unnecessary data movement. Surely there's a better way. Equally, on a processor-intensive operations on fragmented data, you need to pull that data from the storage through the CPU and deliver it to the CPU that wants it so it can do its compute. And again, you're burning cycles doing nothing but moving data around in that CPU that you'd rather have for your data-intensive operations, your compute-intensive operations. So this burden just carries on and causes these issues. You get network congestion over that relatively low bandwidth, expensive, large latencies can become big issues very quickly. And as I said, less CPU cycles and memory cache available for your compute-intensive operations. So these are some subtleties that aren't necessarily always obvious. So, but again, it's not been a problem. You've been quite successful to date with these white box architectures, commodity clusters. So they're still winning out, right? But maybe we've really got a problem coming towards us. And it's great news, really, because storage is getting a lot faster with NVMe. We've seen it with SSDs. It's only getting even faster. And if you take a 24-disk drawer inside a server today, with NVMe drives, you could get 72 gigabytes per second of storage bandwidth. That's huge compared to your systems today. In fact, it's the same size as your memory bandwidth. Now, if we run those same scenarios I just talked to you about in a processor-centric architecture, you completely swamp the CPU, and there's nothing left for you to do compute. So we've got to move to a more data-centric architecture. And this is what IBM really initiated with their OpenPOWER and CAPI. And I want to try and articulate that. So this is pretty much just a fairly similar setup, slightly different speeds, higher speed memory, higher speed disk storage. So the architecture is better to begin with. But really with CAPI, they bring the coherent accelerator processor interface, and they use the PCI transport to be able to actually run this interface. So what does that actually mean? What it really means is they've taken the storage and they've put it on the memory bus, is effectively what's happening with the CAP engine inside. So what JT said about that storage drawer is shown there. So suddenly that burden of the data moving through the CPU is taking off. Not only have they done it there, they've done it with a network controller, so you can actually bring the network straight into the data plane. And then you've got the symmetrical multiprocessing bus for attaching up to 16 Power 8 processors over a very, very high speed, hundreds of times faster than a traditional network bus. So what you can see there is that Power 8 processor, with all the data traffic is now moving through the memory plane, and the Power 8 is actually idle, sat on the side of the memory of the data plane, waiting for the data that it needs to do its work on. So you've got all of those threads are free for your application, not just moving data around. And so the CAPI flash storage, so what we can do, so that's basically articulated what JT said in the current CAPI attached flash storage. But the FPGA, as you can see, that's attaching that in doing the CAPI translation, that's all it's doing. It's translating I/O to storage into this memory, this block memory CAPI attach. And but we're now looking to say, well, okay, what else can we put in that FPGA? So remember, FPGAs are good at streaming and bit manipulation. So we can increase the CAPI flash bandwidth. That's already in progress with more CAPI ports. But we can also introduce acceleration into the FPGA as well as the translation. So we can now, because the FPGA is so good at data processing on data on the move, it can actually consume that 96 gigabytes per second. It's very good at compression, encryption, filtering operations in the, as I said, bit and byte level, and it's extremely power efficient at these operations. So it can do some of the mapper functions, some of the embarrassingly parallel functions, and leave the power rate for the very heavy workload compute functions. So just looking at the some physical implementations, this is the dual power core P822L box that JT briefly mentioned. This is showing the maximum configuration there. We can probably build other configurations actually bigger than that, but this is showing the biggest populated. Each drawer is 56 terabytes of flash. You've got 1 terabyte of memory per processor. These could go as small as 2 terabytes per disk on that, so 8 terabytes per box inside the 2U box. And you've got the 4 gigabytes of bandwidth. So this could be a traditional scale-out Roxy and 4 cluster, a base configuration. We could add acceleration in with the FPGAs, and suddenly we could leverage the much more significant bandwidth to the storage for the mapper parallel functions and the heavy compute. The P8s are there for that. Maybe the balance of this isn't quite right for the functionality, so you might want to add more processors for this. So then if you look at the IBM's E8-17880 architectures, this is the scalable symmetric multiprocessing. So what we're doing here is we're saying, okay, let's look at a scale-out architecture with the FPGAs attached to the disks for doing the mapper type functions, and let's look at a scale-up architecture with very high bandwidth between the processors for doing the compute intensive across the fragmented data sets. So you can see we've got tremendous bandwidths moving around between the processors compared to a traditional network. And you can take that all the way up to a 16-way configuration. So this example is based on the E880. You would get up to 4 terabytes per second to 16 terabytes of memory, and a petabyte of storage at a terabyte per second of access to that storage. So hopefully that's giving you a little bit of a flavor of the directions we're going in with parts of OpenPOWER and where we believe we can bring significant acceleration to HPCC and the ECL. So in summary, HPC systems and OpenPOWER, we're really ready for business. IBM's Power8's data-centric architecture is really ideal for big data problems. FPGAs do provide an ideal streaming near storage accelerator. And if we truly believe we've got an opportunity to re-architect some of the ECL for a Power8 with FPGA acceleration, it will provide a step change in the performance at a lower power and footprint. But it's going to need a community effort. And if there's a call to action from this presentation, it's saying, hey guys, we're ready to go. You guys know the ECL code base far better than IBM or ourselves. And coming to OpenPOWER, join the collaboration, and let's see what we can do with the OpenPOWER architecture. Thanks very much. Questions?
JT, just to make sure I understand, the CAPI interface is independent of the type of flash storage, right? It doesn't have to be any specific type of flash storage.
Currently, it's limited to our IBM flash systems, and that's the current technology that we have is with our our flash systems, what is it, 840, I think, and a 900 drawer. Those are the only two that it works with.
Okay, but is the plan to make it compatible with, or figure out a way by which other flash storage systems can be compatible with it, or is it limited to?
It can certainly be done. We're in conversations with other people to look at other flash technologies,
Okay.
as well as with Nallatech going kind of the next generation he was talking about with the smaller configurations. There's a lot of growth potential there for sure.
Okay, and just one follow-up. Irrespective of FPGA acceleration, did you have to do anything with the HPCC to make it work with CAPI attached flash?
We haven't yet gone to the CAPI flash
got it.
approach. And there will be some work that's done there because the interface to CAPI flash is the block API. It's a block API. So there would have to be some work done on the HPCC software to get it to utilize the block API.
Got you.
Okay. That's it? No,
Thanks very much.
No questions for the hardware guys? Oh, okay, sorry.
So, pretty clearly the end state, or the desirable end state, would be to have some of the ECL compilation produce code for the FPGA. Now, historically, putting new functions in an FPGA, it was pretty slow to write there. Is the state of the art such now that it's possible to have per thread or per process code in an FPGA?
So, a couple of things. It's much quicker. So the OpenCL gives you a C-level language, so you can actually write functions and get to the FPGA really quickly today. Our engineers, we've been porting customers' codes or helping customers port codes for many years. And so our engineers' productivity has gone up dramatically when we use the OpenCL. Okay, so there is that approach. In terms of integrating it all in with OpenPOWER, we're still working through some of that, but it's generally available as a PCI attached, getting it, all the CAPI attached is up and running just, in fact, I is running today, I beg your pardon. But the other approach is you can look at the FPGA as a library function, so you can put functionality in it, and it's a function call to it. And you can blend the two as well. So you can abstract it away from the user more as a function call. In working with Flavio as well, he was saying that potentially you could put some hints in the ECL code itself that could say, hey, go out and use the accelerator for this particular operation. So where the user can have some control over these features.
From the way you're talking around it, it sounds like it still takes possibly a couple of seconds to reflash the FPGA.
No, right. So in terms of functionality from that perspective, you're talking. So you reload the FPGA with a new bit stream for a new function.
Yeah,
so
you want to tailor a filter or adjust.
Yes. So either you can either have them static and running from power up, or you can load them, and there's a dynamic. You actually load through the PCI interface, and so that takes about today that takes a few hundred milliseconds. But partial reconfiguration, this is a little bit more of a future thing. The partial reconfiguration would allow you to load in smaller functions, which would then take in the order of a millisecond or less.
Okay, so the model would be a library, a collection of bits and pieces that could be strung together to make on-the-fly filters.
Right, the on-the-fly filters, the actual compile time of a new design, it's a lot longer to compile for the FPGA, but once you have the bit stream, the load time can be quite fast. And you can have multiple functions buried in it. So if you know you're always going to use encryption and compression in a filter, you could put a programmable filter that has lots of capability across, in one bit stream. So you don't need to reload. You load the computational architecture that you need, and it just stays there for your particular task.
Thank you.
think there was one more question in the middle of the room.
How do you compare CAPI with RDMA? Is there a direct comparison that you can make, or maybe just a conceptual one?
I would say that I probably shouldn't have used it. When you look at the networking side of things, RDMA is becoming very popular. And what RDMA allows you to do is for the traditionally I/O devices and processor cores weren't able to share memory just because of deadlock cases and the lack of coherency, et cetera. RDMA in the networking side has created the ability for you to share application memory, to share virtual memory essentially. And CAPI takes it to the next level because with RDMA you still have to recode your application there's special memory allocation schemes to get memory for RDMA to share. But with CAPI, when you want to share memory, you just malloc or whatever. You just use standard memory allocation routines and then just point the CAPI attached device to that memory. There's no overhead. It makes the code changes a lot less invasive because it's truly shared virtual memory. There's no special libraries behind it. There's no device driver at all.
So could it be abstracted over an RDMA capable device? Like, can you have a Mellanox card there that you can
So what
CAPI?
Mellanox is actually, they've got the RDMA technology. They are also going to do a CAPI device as well. And the reason that they're doing that is because RDMA is, like we said, it's great, but it's hard to adopt. It's hard to get people to go change their code base. It's very difficult to do that. So with CAPI, they can take the same advantages of having shared memory to reduce latency and increase performance, but do it without any rip up to application code. So that's one of the key differences between RDMA and CAPI. That's a good question. I think there was one more question.
Hi.
No? Okay.
If HP comes through with their memory store technology, what will be the impact on CAPI Flash?
I'm sorry, I didn't hear.
If HP comes through with their memory store technology, what will be the impact on CAPI Flash?
That's a good question. That is going to be it is a disruptive technology for sure, right? But there still are trade-offs because the way that is going to fit in, it's still unclear how to make it work because of right now, when you look at Flash, it's hard to get people to think about anything other than memory and disk, right? And so when you introduce that technology, sure, you can replace all of your DDR memory with this new technology, but you are going to lose performance. It's not as fast as DRAM, right? So you can make a choice where either you come up with some three-tiered scheme now where you have DRAM, traditional memory, then there's something that looks kind of like memory, and then storage, which is it's going to be a lot harder to adapt. Or you can replace your DRAM with this new technology. And there are certainly going to be cases where that's going to win. And yes, that is going to be disruptive. We think that with the CAPI Flash, we have a similar technology. The cost is going to be probably comparable, and the performance might be a little less, but we have a lot more flexibility.
I think the key message there, and what IBM have really done with CAPI Flash is they're making storage look more like memory. Memory is storage, storage is memory. Why do we categorize the two differently? That's a historic reason, and for good reason with spinning disks, but suddenly memory, they're beginning to treat storage like memory. When you guys move to in-memory databases, suddenly you tripped over, you say that the persistence problem with these big databases, so therefore you attach Flash for backup when power was lost. So if you look at the transition over the last good few years, we are beginning to say, let's just treat this all as memory. And so you're talking about another tier of memory that sits between us between DRAM and storage and Flash.
Thanks, Flavio. Thank you. Thank you, Allan. Very good. This was cool. I hope it wasn't too deep into the metal for those that are more software-centric. But I thought it was a very good presentation on not just what we can do today, but also what we could do in future. And this might be a way to really leap forward if we decide to adopt this type of technologies. Now, couple things. One is, for those in the live stream, remember, tweet, the hashtag HPCC Summit. For others, we will see a great presentation now from people in KSU, in Kennesaw State University. This is, and let's see, if I say this is about statistics, someone will say, oh, boring. But how about machine learning? Oh, that sounds kind of interesting. Deep learning, oh, that's even cooler. And if I say artificial intelligence, oh, that's really cool. So help me welcome Ying, and Pooja Chenna from Kennesaw State University. They're going to do a good presentation on machine learning and deep learning on HPCC.
Good morning, everyone. I'm Ying from Kennesaw State University, and this is Pooja Chenna, my graduate student. So we will co-present the studies of HPCC systems from machine learning perspectives. So first, we will talk about how we leverage and enhance deep learning capability of HPCC systems. Then we will present a comparative study of HPCC systems and the newest version of Hadoop systems. So deep learning has been emerged as a recent breakthrough in the area of machine learning and has revitalized research activities in artificial intelligence. So we know that the development of deep learning actually has been primarily driven by big data and analytics. So since that HPC system is a well-established big data platform, so I think it's very important actually for us to leverage and enhance the deep learning capability of HPCC systems. So let me just briefly introduce deep learning techniques. So what I have on the slides here is a typical multi-layer perceptron, right? So we can use the well-known backpropagation algorithm to train this neural network. As long as we have enough hidden neurons in the middle, then this multi-layer perceptron actually can approximate any function. So this is also called a universal function approximator. But the major problem of multi-layer perceptron is it may overfitting with the training data, right? So instead of using many hidden neurons in the middle layers, researchers have proposed a deep architecture of a neural network like this. Okay, so we have many layers of the networks. One of the benefits for this deep architecture is that we can extract high-level features from the raw data. Okay, then we can make decisions based on the high-level features instead of on the raw data. So in terms of image classification, for example, we can extract the high-level features by using the deep architecture, something like face, body, walking, running, or something like that. Then we can do the classification based on those high-level features instead of the pixels, right? So this pretty much aligns with how human perceives the object, okay? But one of the biggest challenges for deep architecture like this is how to train this neural network with the deep architectures. Because backpropagation is no longer effective given the vanishing gradient problem. Okay, so since the year 2006, researchers have proposed using unsupervised learning to train the deep architecture layer by layer independently. Okay, so it depends on different unsupervised learning algorithms used to train layer by layer for the deep architecture. We have different actually deep architectures for neural network. So one of them is called a stacked autoencoder. So this is how stacked autoencoder works. So in the top, we have the deep architecture. Again, we train them layer by layer, right? When we train the first layer, for example, we expand it into the bottom autoencoder. So for this autoencoder, the input neuron will be first compressed to the hidden layer. Then the hidden layer will be decompressed to the output layer, right? So we can use backpropagation to learn the weights for this autoencoder with the expectation that the data generated by the output layer will be the same as the input neuron. Okay, then we use the same technology to train each layer of the top architecture layer by layer. So actually, the stacked autoencoder has been implemented using ECL on HPCC systems by Marianne from Florida Atlantic University. So this is the ECL code for this is freely available on GitHub. And another well-known deep architecture is called deep beneath network. So for deep beneath network, actually, every layer can be viewed as a restricted Boltzmann machine. Restricted Boltzmann machine actually is a probability model, right? So given the training data or the observations, so we learn the weights such that we generate a hidden layer that we can maximize the likelihood of the observation. We can use some technology like one-step Gibbs sampling, or also called the contrastive divergence, okay, to learn the weights for the restricted Boltzmann machine. Actually, we implemented this restricted Boltzmann machine and the contrastive divergence in ECL on HPCC. And we also implemented the deep beneath network, which is a stacked version of restricted Boltzmann machine. So later on, Pooja will talk about some implementation details for the deep beneath network. So now, we will talk about how we use the deep architectures that we implemented to visualize high-dimensional data. So you may know that given a high-dimensional data set, right? So it's very hard for the user to gain insight into the data because of the high dimensions, right? So, but if we can visualize the high-dimensional data, then things change dramatically, right? So let's use a very simple example to illustrate. So this is iris data. Actually, this is not real high-dimensional data. We only have 4 dimensions here, right, with 3 classes. So what we can do is we use the deep beneath network that we implemented on HPCC to transform this data into 3 dimensions, okay? So once we transform the data into 3 dimensions, then we can visualize it in the 3-dimensional spaces. So you can see this visualization actually shows that these 3 classes are well separated. So by viewing this visualization, you may imagine that we can easily use logistic regression or something like that to separate one class from the other, right? So typical machine learning packages will visualize data like this by picking 2 dimensions at a time and visualize it with the class label. But this type of projection is very hard for a user to gain the overall picture for the structure of the data, right? But if we can visualize in this way, immediately you have better feeling of the data, right? So this is just another angle to view the data. Okay, so this is another data set that we tested out, Wisconsin breast cancer data. So this data has 9 dimensions with 2 classes, benign cases and malignant cases, right? Again, by viewing this table, it's really hard for user to gain any insights. So what the user can do, maybe run some class-trained algorithms to find out how the records are related to each other, or run naive Bayes to find out how the attributes are correlated to each other. But still, it's hard to gain any insights into the data. But now, we use deep beneath networks that we implemented on HPCC to transform the data, first from the 9 dimensions to 7 dimensions, then from 7 dimensions to 5 dimensions, then to 3 dimensions. Then we can visualize it, right? So once we visualize the data, then immediately we gain much better about the structure of the data, right? So you can imagine that we have a new patient, okay? So what we can do is we transform that record into 3 dimensions, then plot into this space. If that new instance is in this yellow area, immediately you can say that the risk is low. If it's in that blue area, the risk may be high, right? So in other words, you can actually make visual decisions with a visualization like this, right? So this is just another angle to view the same data set. So this is another data set with 6 classes, right? So this time we use a stacked autoencoder to transform the data into 3-dimensional space and visualize it. So we get a visualization like this. From this visualization, we find that actually the 6 classes are mixed together. It's really hard to differentiate one class from the other, right? So by viewing this data, of course, we can view this data from different angles, right? By viewing this data, I'm just thinking that since it's hard to draw any decision boundaries between the classes, right? Maybe the nearest labels algorithm works well for classification. Okay, so in order to test this hypothesis, we just run different machine learning algorithms on this data set. And we really find that actually the 3 nearest label algorithm gives the best results actually. So the second column of this table actually shows the number of misclassified instances generated by different machine learning algorithms. So you can see that 3 nearest label actually generated the least number of misclassified instances. So what does this mean is, with the visualization of the high-dimensional data, actually, the user can gain some feelings of what machine learning algorithm may work for this data set. Okay? So not only we can transform the data from high dimension to lower dimensions, then we can visualize the data. We can also map the data from its original space to even higher dimensional space. Okay? So here is an example. This is blood transfusion data, 4 dimensions. So we use both the deep BNF network and the stacked autoencoder to map the data from its original dimensional space to a higher dimensional space, which is 10 dimensions. Then we run machine learning algorithms on both the higher dimensional space and its original dimensional space. We compare the results, right? So we find out that for both DBN transformation and the stacked autoencoder transformation, actually the higher dimensional space, the 10 dimensional space, the machine learning algorithm works best. Okay, works better. Okay. This is another example. We have the wine data, 13 dimensions. Okay. Then we use the deep architecture we implemented on HPCC to map it to 15 dimensions. Okay, then we run machine learning algorithms on both dimensions to say which one actually works better. Then we found that actually the higher dimensions works better again. Okay, but not always like this, right? So we test a bunch of data sets, so then we found out that for some data sets, higher dimensional space actually works better, but for other data sets, lower dimensional space actually works better. So here is an example. So for this breast cancer data, okay, its original space is 9 dimension, okay? So we use a deep architecture we implemented on HPCC to map the data to 3 dimensions, 6 dimensions, and 12 dimensions, right? Then we find out actually the 3-dimension space works best for this data set. So we form a hypothesis. So for data sets which are noisy, when we transform the data sets to lower dimensions, we may filter out a lot of noise. So therefore, maybe lower dimension data set, the lower dimension space works better. Okay, for a data set with a lot of correlation between attributes, okay, when we transform the data into higher dimensional space, we may break those correlations. Okay, then therefore, the higher dimensional space may work better. So we will further test our hypothesis theoretically or empirically in a future study. Okay. So our next step, we try to implement a meta-learning strategy on HPCC by using ECL. So how this meta-learning strategy works? So given a data set, okay, we automatically map this data set from its original space to multiple other dimensional spaces, some higher and some lower. Okay? Then we build the machine learning models on all these spaces in a distributed way by using HPCC. Okay? HPCC, because it's a distributed platform, so it's very good at this type of parallel task. Right? So once we build the models on different spaces, then we use cross-validation to pick the optimal space with the best model. Then we present that model to the user to make further decision or predictions, right? So our fundamental goal is to really implement a deep learning engine for HPCC such that you can just use that for all the data analysis, like image analysis, text analysis, and so on. With that being said, I will hand it over to Pooja, so she will talk about some implementation details of deep belief network using ECL on HPCC.
Thank you, Dr. G, for explaining us an overview on deep learning, deep belief networks, and then its applications like visualizations, realizations on 3D spaces. So now I'm here to talk to you about deep belief network and how it is implemented in HPCC systems. So before I go for deep belief networks, maybe I'll introduce restricted Boltzmann machine, then deep belief networks, and more improved version called supervised deep belief network. So why restricted Boltzmann machine? Because it is a building block for deep belief networks. It is just a 2-layer neural network that I first built it with an algorithm called contrastive divergence. Then I stack all those together to form the second one, the deep belief network. And then we performed a lot of experiments with this deep belief network, which we have already shown previously. So when we thought the original results are very much comparable with the results from deep belief network, so we want to improve the architecture more, the deep belief network architecture. So originally, the training is layer by layer, unsupervised training for deep belief network. So what we have done is make it supervised. So what happens when it becomes supervised? So the results will be much better. So we are investigating on that. We have improved the architecture of the deep belief network and working on that. So I need not work on the lower level aspects like matrix manipulations, calculations, or the parallel block blast operations and all. So I just picked whatever I want from these machine learning routines, which are already available in HPCC systems, and directly used them in my implementation. So the first one is restricted Boltzmann machine. So it uses an algorithm called contrastive divergence. So here you can see 2-layer network. The first layer, the bottom layer, is the visible layer, and the next layer is the output layer, or the hidden layer, which has the confabulations similar to the visible layer. So when I use the weights and bias from the visible layer, I get the output at hidden layer. I use the same output to get, in the reverse manner, to get the confabulations at the visible layer. So this process goes on repeated till the algorithm completes, that is, till I get the second confabulation at the hidden layer. So when I have all these things at hand, then I go further to modify the weights and bias using gradient computation. So this is ECL code, a sample code which I have put here, which processes the forward and backward manipulations and get the output at this visible and hidden layers. So this is how the gradient is computed and weights and bias are updated after I go through the contrastive divergence algorithm. So initially, we have gone through the formula mentioned here, the confabulations difference multiplied by alpha. Alpha is the learning rate, which can be chosen by the user. And if a few data sets, it would be better if it is very small, and few other bit higher than that. So usually, it may be something like 0.1, 0.5, something like that. So when we used this in the experiments, we found that the results are not that good for deep belief networks. So what we have gone through is we want to reduce the error rate and improve the results. So we have gone through a mini batch gradient descent technique. So what a mini batch gradient descent technique does is it splits the whole input into a lot of batches and does the processing batch-wise. So in that way, the weights are more improved, the error rate is reduced, and the results are more significant than previously. So there's one more routine called split input. This actually shows the whole process of the Boltzmann machine learning. So initially, we split the whole input based on the batch size, and then we do the forward, reverse, and forward propagations to get the confabulations, then finally calculate the differences, compute the weights, compute the bias, and finally get the output from the Boltzmann machine. So once I have that output at hand, now I would use it further to get it into, use it into deep belief network. That is, the initial output from one Boltzmann machine, I use it for the next Boltzmann machine, and the learning process of contrastive divergence repeats, and that output is given to the next RBM. So this process repeats till all the Boltzmann machines' learning is completely done. So finally, the output at the last layer or the last Boltzmann machine would be the output of the deep belief network. So this is how the looping or stacking of Boltzmann machine is done to form the deep belief network. So after this point, we further try to improve the architecture because we have seen the results. These are just a sample output from the iris data, which we have seen the realization earlier. The 3 classes of this iris dataset were clearly separated. So here we have taken a 4-layered 4-3 architecture. That means 4 neurons in the hidden layer, 4 neurons in the input layer, and 3 neurons in the output layer. So I got the 3-dimensional output, if you can see here, see there. So it is reduced through 3 dimensions from 4 dimensions. So this output, when I feed it into the neural network to get the classification results, it was much closer to the original results, but still better. So we have improved it further using this supervised learning technique. That means we use the layer-by-layer supervised technique. The red color highlighted part would be the attached output layer. That is the actual output. But the bottom 2 layers are nothing but just the Boltzmann machine. So I use that output layer to compare with the output which I got from the Boltzmann machine to reduce the error rate further. So it goes through 2 techniques. One, supervised fine-tuning method, and then perceptron learning technique backpropagation. So using these both, we thought the errors would be much reduced and we would get much significant output. So we are still investigating on the experiments and results of this supervised deep belief network, but this is just a snapshot of the code, how the supervised deep belief network is implemented. So it first calls the deep belief network. It treats the whole network as a deep belief network. It processes through contrastive divergence, and the final line, if you could see, that is perceptron learning, which is already there and implemented in ECL. So we would use these both and finally get the output for the supervised deep belief network. And we think the results to be much better than the original results and the deep belief network results. So this brings almost end to the study or research which we have conducted on deep learning. So our ultimate goal is to implement a full stack of deep learning algorithms on HPCC platform and conduct a wide range of experiences to show how powerful the deep learning engine on HPCC will be. So at this point, I would like to mention quite few names who has helped us in ECL issues which we faced and deploying a cluster, KSU HPCC cluster, the team from LexisNexis HPCC Systems, and the trainer who got my ECL concepts clear, Bob Foreman and Richard Taylor. Thank you. This was I was talking about. This is the next aspect of our presentation, HPCC and Hadoop comparison results. So we have performed a lot of experiments on both Hadoop and HPCC because previously we were using Hadoop, and now we have moved on to HPCC and conducted the same experiments which we have conducted previously in HPCC. And we made sure that both the platforms are of equal configuration. So we have taken HPCC cluster with 5 Thor nodes and Hadoop cluster with 1 job tracker and 4 worker nodes or task trackers. So we made the configuration similar, and we did both experiments. We have taken a wide range of algorithms from each category for comparison: text processing algorithms, machine learning algorithms, and graph algorithms. So from all of these categories, we have chosen one algorithm and did experiments on both the platforms. So the results were almost pretty much same, and HPCC outperformed in most of the cases. So I would like to proceed with the text processing algorithms. The first one, here the data was authorized version of Burble downloaded from the link which you can see there. So this is the whole Bible actually. So the same input is used for conducting experiments on for both the algorithms word count and inverter index. So the HPCC implementation actually is done by David Baylis. He's a chief data scientist and VP of LexisNexis Risk Solutions. And Hadoop Inverter Index, it's from the reference given there. So what we have done is to make the comparison fair, we have ignored and discarded our own implementations because there was not much optimization in our code. So what we thought is the comparison has to be fair. So for Hadoop, machine learning, and others, we have used reference and Apache Mahout newest version library, and HPCC, few of the implementations which are done by us and few of the references. So here the word count, as you can see, it's just done in 1.003 seconds to process the whole Bible. And for Hadoop, it was 23.466 seconds. And for inverter index, it is almost similar, but the HPCC took 34.205 seconds, and Hadoop took 27.04 seconds. So for machine learning algorithms, as I mentioned earlier, it is the newest version of Hadoop Apache Mahout. And for HPCC, it's the machine learning library of HPCC. The input data is the KDD network intrusion data set. The reference is given there. And it has a lot of samples, actually. So what we have done is we have randomly picked some 20,000 instances and did our experiments. The attributes are also, there are a lot of dimensions, 42 dimensions here. So the efficiency is like random forest. Maybe some optimization is needed in HPCC in this context. So it took 1 minute, 50 seconds. Well, and Hadoop Apache Mahout, it is just 18 seconds. And K-means, it is 36.675 seconds for HPCC, and 1 minute and more for Hadoop, 1 minute, 45 seconds. The graph algorithm, so we have a Java implementation which randomly generates the graph with the given number of nodes and degrees. So we have randomly generated a graph with 25 nodes and maximum degree as 5. So we fed that input to both HPCC and Hadoop platforms. HPCC, we have done our own implementation for page ranking, whereas Hadoop, we have used a wiki page ranking algorithm, and we have seen that HPCC, it's just 29.817 seconds to give the result for 25 nodes graph, a big graph. But Hadoop, it was 36 minutes. Maybe that the Hadoop code which we have used is not that optimized, so there's a lot of difference here. So I think this is the pretty much end of the presentation which we have done. It includes all the research we have done for both deep learning and the comparison part of HPCC and Hadoop. So thank you, and
yeah, any question or comments?
Hello.
Yes.
The machine learning is a charming place. So actually, I have two questions. Because in here, you do a lot of decreased dimension. But you know, when we do the decreased dimension, the sufficiency dimension is very important. So I'm wondering whether you can expose how you do to this judgment. Second thing is that when we do the sufficiency dimension, the training sets is very important. That means it's case by case, depends on your training sets. If we for the industry, mostly the training set is very dynamic. So on that area, can you give some idea how to enable that?
Sure. Very good question. So I will start with the second question. He mentioned that the training size is a problem for the real world, right? So that's true. See, that is one of the biggest points we use deep learning. When we use deep learning, actually, we can take advantage of those huge amount of unlabeled data. Because just like I mentioned, right? So how we train the deep architectures? We train the deep architectures layer by layer by using unsupervised learning. So when we train the neural networks, actually, we don't need the labeled data. So we know that sometimes the labeled data are very expensive, right? It's very hard to get. But by using deep learning, we can train the neural networks by using leverages unsupervised using unlabeled data. Then if you have a small set of labeled data, then we can just put that on to form a final perceptron, then to just do some final refine. So in this case, actually, for the situation where you don't have much labeled data, deep learning is a great tool to use. Then come back to the first question. When we reduce the dimensions from high dimension space to lower dimensional space, how we reserve the structures. So by testing a bunch of data, so we find out it's amazingly, although we can reduce dimension dramatically to 3 dimensions in order to visualize it, but after we visualize it, we find out that actually the structure of the data are preserved very well. Why we know that? Because we have the training data, right? So we also do the classification on the lower dimensional space. So we find that actually the data, the different classes are separated very well. So that's how we feel confident on this dimension reduction. And also another thing is like actually we do more tests than what we put on the slides. So once we reduce them to the 3-dimensional spaces, we also conducted classification on the lower dimensional space, and we find that actually the result for some of them really show it's better, but for those who are not better, actually is very comparable to the original space. So we find that actually deep learning is really doing a good job to keep the structure of the data when we do the dimension reduction. I hope that answers your questions. Any more questions?
When you do dimensional reduction, do you constrain for orthogonality?
Constrain for one, sorry, can you repeat again?
When you reduce to, say, 3 dimensions, do you force them to be particularly orthogonal?
Particular?
Independent of each other?
Independent of each other?
Yeah.
No, we don't constrain anything. We just use the deep architectures to map the data from the original space to 3 dimensions. So there may be correlations between, I think maybe correlations between the 3 dimensions. So we don't have any constraints, basically.
Okay, and then when you add dimensions, they are probably highly correlated.
Yeah, when we map them to higher dimensional spaces, I think, this is my hypothesis again, I think some correlations between the attributes in the original space actually has been broken in the high dimensional space. So that's why in the higher dimensional space, actually, sometimes we have better performance.
Thank you.
Thank you. Thank you very much.
Thank
for
you.
your attention.
Okay, so you probably agree with me that was a good presentation. How many of you are involved or have knowledge of machine learning? Can you raise your hands? Machine learning in general? Quite a few. How about neural networks or stratified classifiers? Some of you, good. How about deep learning and deep belief networks? Okay, even less. Okay, so I think this is a good overview and also paints a good picture on what they have done already and what's coming in this area in HPCC. Besides, in addition to this, we have some good work going on. I mentioned at the beginning with Imperial College, they are going to be working on implementing some additional classifiers for deep belief networks for NLP, for text extraction on medical records particularly. So we'll see something coming from that too. Very good. So now, our live streaming people, we will be coming back in at about 12:30. So it's going to be in 30 minutes from now. So just take a break, go grab some food, and be ready to start again at 12:30 Eastern. For the others, we will have food outside. So please walk, don't race to the food. But try to be back